Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the area of this rectangle ABCD, and in the second question, we'll find out the area of this green shape that is inside square ABCD. So we'll start with the first question. In the drawing, we have rectangle ABCD. Inside this rectangle ABCD, we have this semicircle. This is line segment AEP, that is equal to 6 units in its length. This is line segment PC, that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So ABCD is a rectangle, therefore all those four angles inside the rectangle ABCD are right angles. So actually, this angle equals to 90 degrees in its size. This angle also equals to 90 degrees in its size. This is a right angle. This is also a right angle. In the next step, we will define the radius. We define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. And we define the point of tendency of tangent DC with this semicircle. This point as point M. We will define the touching point of this semicircle with side AB of rectangle ABCD. This point is point E. In the next step, we join points O and M together by a straight line. Point O is the center of this semicircle. Point M is a point on the semicircle itself. Therefore, OM is the radius of this semicircle. Is equal to x units in its length according to our definition. And because of the fact that the radius OM that is equal to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. By doing this construction, if you together there, quadrangle MCBO. Inside this quadrangle MCBO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again. In total, they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, these 4 pieces again must be equal to 90 degrees in its size. So inside quadrilateral MOBC, we have right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle plus a square. So relate to this quadrilateral, it's rectangle because it has 4 right angles. So I write it down. This quadrilateral MCBO is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle MOBC, side MO must be equal to the opposite side CB. But MO is x, therefore the opposite side CB must be also equal to x units in its length. In the next step, we join points P and A together. We join points P and E together by a straight line. By joining points P and E, we get a angle APE. This is peripheral APE that subtend on AE, that is the diameter of this semicircle, and according to Rule 7, any peripheral angle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. So I'll pick quickly on Rule 7. According to Rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees. In the drawing, we know that the diameter of this circle is AB. This is peripheral angle ACB that subtend on AB, that is the diameter of this circle. And therefore, according to this Rule 7, peripheral angle ACB must be equal to 90 degrees in its size. So what we mentioned before, can implement Rule 7 in our drawing. Why? Because in our drawing, this is peripheral angle APE that subtend on AE, that is the diameter of this semicircle, and therefore peripheral angle APE is equal to 90 degrees in its size according to Rule 7. In the next step, we define this angle as alpha. So in triangle, the right triangle APE, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. Well, because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. So, in the next step, we will prove that the big right triangle ABC is similar to this small right triangle, triangle APE. So, write it down. We prove that the big right triangle, triangle ABC, is similar to the small right triangle, triangle APE. But before that, this is angle A, that is a common angle that belongs to both triangles. It is very easy to see from the drawing that angle A belongs to the big right triangle ABC, and angle A belongs also to the small right triangle, triangle AP. So angle A is a common angle that belongs to both triangles. So why the big right triangle ABC is similar to this small right triangle APE? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So actually, this is angle ABC. In the right triangle ABC, and it is equal to this angle, that is actually angle APE. In the right triangle APE. Now, so I'll repeat again. Actually found out that angle ABC in the right big triangle ABC equals to angle APE in the small right triangle APE. They are both equal to 90 degrees, and therefore they are equal to each other. In addition, as I already mentioned before, this is angle A, that is a common angle that belongs to both triangles. So we can write down that angle A equals to itself as a common angle that belongs to both triangles. So if we relate to this angle A, since it belongs to the big right triangle ABC, it will be defined as angle BAC. And angle A equals to itself. So if we relate to this angle A, as it is belongs to the small right triangle APE, it will be defined as angle EAP. So repeat again. This equation means that angle A equals to itself. We just call to angle A two different names. Angle A equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So okay, this is angle BCA. In the right big triangle ABC, and it is equal to this angle, that is actually angle PEA. In the right small triangle PAPE. So repeat again. Angle BCA in the big right triangle ABC is equal to angle PEA in the small right triangle APE. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the triangles inside the big right triangle ABC are correspondingly equal to all the triangles in this small right triangle APE. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I'll write it down. We can find out that the big right triangle ABC is similar, this is the sign of similar, to the small right triangle APE according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the small right triangle APE over side AB of the big right triangle ABC is equal to side AE of the small right triangle APE over side CA of the big right triangle ABC. So repeat again, from the fact that triangle APE is similar to the big right triangle ABC, we will derive that the following relationship exists between their sides. That side AP of the small right triangle APE over side AB of the big right triangle ABC is equal to side AE of the small right triangle APE over side CA of the big right triangle ABC. AP equals to 6 units in its length according to what is given us the question, over AB. AB is the missing side, so we leave it as it is, and it is equal to AE. AE is the diameter of this semicircle. AO is the radius of this semicircle, that is equal to X. OE is also the radius of this semicircle, that is also equals to X. So in total, AE equals to X plus X, that is 2X. It is the diameter of this semicircle. If the radius is X, the diameter is 2X, of course. So AE equals to 2X over CA. CA in total equals to 5 plus 6, that is 11. So CA is 11. So in total, we actually found out that 6 over AB equals to 2X over 11. Here we will cross multiply this equation, and we get that 11 times 6 equals to 2x times AB. 11 times 6 is 66, so 66 equals to 2x times AB. Here we will divide this equation by 2, and we get that 66 over 2 is 33, so 33 equals to 2x over 2 is x times AB. Here we will divide this equation by x. It is allowable to divide the equation by x because x is the radius of this semicircle. It must be a positive number, it can never be equal to 0. So it is allowable to divide this equation by x. And we get that AB equals to 33 over x. So the length of this side AB of rectangle ABCD is 33 over x. AB is actually the length of this rectangle ABCD, while BC is the width. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle is equal to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length is AB, and the width is CB. So in total, we found out that the area of rectangle ABCD equals to AB times CB. AB is 33 over x, and CB is the width, that is x. So in total, we found out that the area of rectangle ABCD equals to 33 over x times x. We have x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. So in conclusion, we found out that the area that we are looking for in this question, that is the area of this rectangle ABCD, is equal to 33 square units. So we finish with the first question. In the next step, I will present to you the second question, and we will solve the second question of this lecture. Our mission in this second question is to find out the area of this green shape. In the drawing, we have a square ABCD. ABCD is a square. In addition, we know that the area of this triangle OPC is equal to 5 square units in its size, and also BP equals to PC. Again, our mission is to find out the area of this green shape. So, first of all, we will define the length of BP as A. If BP is A, PC must be also equal to A because they are equal to each other. We know that all the sides of any square are equal to each other. So if BC equals to 2A, then AD must be also equal to 2A. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this angle is theta, then the size of this angle must be also equal to theta because they are equal to each other according to the rule that I mentioned. Vertex angles are equal to each other. We know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to the opposite side BC. Those two angles, they are defined as alternating angles, and they are located between the parallel lines AD and BC, and therefore they are equal to each other according to rule 15. So if this angle is beta, if this angle is alpha, then this angle must be also equal to alpha because they are equal to each other according to rule 15. Likewise, those two angles, they are also define these alternating angles, and they are located between the parallel lines AD and BC, and therefore according to rule 15 they must be equal to each other. So if the size of this angle is beta, then the size of this angle must be also equal to beta according to rule 15. Rule 15 states that alternating angles between parallel lines are equal to each other. Those two alternating angles that are located between those two parallel lines AD and BC must be equal to each other. So if one angle is beta, then the angle must be also equal to beta. So it is very easy to see that once we found out that the big triangle AOD is similar to the small triangle POC. Why? Because they have exactly the same angles. Those two angles are both theta, those two angles are both alpha, and those two angles are both beta. Therefore, the big triangle ADO is similar to the small triangle POC according to angle similarity rule. So I write it down. The big triangle ADO is similar, this is the sign of similar, to the small triangle POC, according to angle similarity rule. And from the fact that those two triangles similar to each other, we will derive that actually we must, I will present to you rule 22, and we will implement rule 22 in our drawing. According to rule 22, the ratio of the two, the ratio of the areas of similar triangles is equal to the square of the ratio of their sides. So in the drawing, this is triangle ABC that is similar to this triangle ADE. Triangle ABC is similar to triangle AD. Therefore, the ratio between the areas of those two triangles, that is actually the area of triangle ABC over the area of triangle EDF, will be equal to the square of the ratio of their sides. The square of the ratio of their corresponding sides. That is to say, it will be equal to AC over DE square, and it is also will be equal to AB over DF square, and it is also will be equal to CB over EF square. So the square, the ratio between the areas of this triangle will be equal to the square of the ratio of the corresponding sides. Okay, so I can actually implement rule 22 in our drawing. Why? Because in our drawing, we actually found out that the area of this big, the big triangle AOC is similar to the small triangle COP according to angle similarity rule. Now we can implement here rule 22. According to rule 22, the ratio between the areas of those two similar triangles, this is actually the area of triangle DOA, so the area of triangle DOA over the area of the small triangle POC. That is the ratio between the areas of the two similar triangles, is equal to the square of the ratio of their corresponding sides. Side AD is the corresponding side of side PC, so the ratio is AD over PC squared. AD over PC squared. So actually, this equation is the implementation of Rule 22 in our drawing. Again, the ratio between the areas of the two similar triangles is the area of triangle DOA over the area of triangle POC, and it is equal to the square of the ratio of their sides, of their corresponding sides. The corresponding sides are AD and PC. Therefore, it is AD over PC squared. Okay? The area of the big triangle ADO is the missing area, so we leave it as it is. So it is the area of triangle DOA over the area of triangle POC. It is given us in the question that the area of this small triangle POC is 5 square units. So let's substitute the area of triangle POC by 5, and it is equal to AD over PC squared. AD is 2A over PC. PC is A squared. We have A in the denominator and A in the denominator, so A will get cancelled. We get cancelled, and we left only with 2. 2 squared is 4. So in total, we should find out that the area of triangle DOA over 5 equals to 4. Here we will multiply this equation by 5, and we get that the area of triangle DOA is equal to 4 times 5, that is 20. So we found out that the area of the big triangle, triangle DOA, is equal to 20 square units. The area of this big triangle, triangle DOA, is equal to 20 square units. So write it down, it is equal to 20 square units. Okay. Because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. That is to say, side AD of triangle ADO over side PC of the small triangle POC is equal to side AO of the big triangle AOD over side OC of the small triangle COP. So in total, we found out that AD over PC, AD is 2A over PC. PC is A. So it is 2A over A is equal to AO over OC. We have A in the denominator and A in the denominator, so A will get cancelled, and we left only with 2, that is equal to AO over OC. Here we will multiply this equation by OC, and we get that 2 times OC is equal to AO. If we define OC as B, so here we substitute in this equation OC by B, and we get that 2 times B equals to AO. So actually, we found out that if AOC is B, then AO is 2B. Repeat again, if OC equals to B units in its length, then AO equals to 2B. Okay, so in the next step, I'll present to you a new rule, and we will implement the new rule in our drawing. The new rule is true in any triangle. This is triangle ABC that could be any triangle. If you draw this red line segment AP inside this triangle ABC, it will divide triangle ABC into two parts. Actually, it will divide triangle ABC into two smaller triangles. The first triangle will be triangle APB, and the second triangle will be triangle APC. The area of this triangle ABP equals to the base of the triangle that is BP times the height that is edge divided by 2. I repeat again, the area of this triangle ABP is equal to the base BP times the height edge over 2. The area of this triangle APC is equal to the base that is PC times the height that is edge. Both triangles have the same height that is edge, divided by 2. So the area of triangle APC is the base PC times the height that is edge divided by 2. Now the ratio between the two areas is the area of triangle ABP over the area of triangle APC. The area of triangle ABP is BC times edge over 2, while the area of triangle ABC is CP times edge over 2. We have 1/2 in the numerator and 1/2 in the denominator, so 1/2 will get cancelled. We have edge in the numerator and edge in the denominator, so edge also will get cancelled, and we're left only with BP over CP. So in conclusion, we can say that if we divide triangle ABC into two smaller triangles, and then the ratio between the two smaller triangles is equal to the ratio between their bases. Well, it is BP, that is the base of triangle ABP, over PC, that is the base of triangle APC. So the ratio between the two triangles is equal to the ratio between their bases. So we can actually implement the new rule in our drawing. Why? Because in our drawing we have the right triangle ADC. The right triangle ADC is divided into two smaller triangles by line segment OD. By drawing line segment OD, we divided the big right triangle ADC into two smaller triangles. The first triangle is triangle ADO, and the second triangle is triangle OCD. So according to the new rule, the ratio between the areas of those two triangles, that is to say the area of triangle ADO over the area of triangle OCD, will be equal to the ratio between the bases of those two triangles. We take the base of this triangle ADO as AO, and we take the base of this triangle OCD as OC. So according to the new rule, the area, the ratio line segment OC divides the big right triangle ADC into two smaller triangles, triangle AOD and triangle OCD. The ratio of those two smaller triangles is the area of triangle ADO over the area of triangle OCD. And the ratio between the areas of those two smaller triangles, it is equal to the ratio between their bases. The base of this triangle AOD is AO, and the base of this triangle OCD is OC. So this equation is the implementation of the new rule in our drawing. So if you found out that the area of triangle ADO or the area of triangle OCD is equals to AO over OC. But we have already found out that the area of triangle ADO is 20 over the area of triangle OCD. The area of triangle OCD is unknown, so we leave it as it is. And it is equal to AO. AO is 2B. AO is 2B over OC. OC is B according to our definition. This is 2B over B. So we have B the numerator and B the denominator, so B will get cancelled and we left only with 2. So here we divide this equation by 2. We divide this equation by 2, we will multiply it simultaneously. We cross multiply it. So we get that 20 over 2 equals to the area of triangle OCD. Again, we divided this equation by 2 and then we multiply it by OCD. So in total we found out that the area of triangle OCD equals to 20 over 2, that is 10. And again we found out that the area of triangle OCD is equal to 10 square units. The area of this small triangle OCD is equal to 10 square units. Triangle ADC, the right triangle ADC, congruent to the right triangle ABC according to side rule. Because of the fact that ABCD is a square, side AD equals to side BC. So side AD of triangle ADC is equal to side BC of triangle ABC. Likewise, side DC of triangle ADC is equal to side AB of triangle ABC. And finally, side AC is the common side that belongs to both triangles, so AC equals to itself. So if you prove that triangle ADC is congruent to triangle ABC according to side rule. So I write it down. We actually found out that the right triangle ADC congruent, this is the sign of congruent, to the right triangle ABC according to side rule. All the three sides of triangle ABC are correspondingly equal to all the three sides of triangle ADC. Therefore, the two right triangles can go to each other according to side rule. And therefore, because of the fact that they can go into each other, they must also have the same areas. That is to say, the area of the right triangle ADC is equal to the area of triangle ABC. But the area of this right triangle ADC is 20 plus 10, that is 30. So we can write here that the area of triangle ADC is 30 square units. And from this equation, 30 equals to the area of triangle ADC equals to the area of triangle ABC. We will derive that the area of triangle ABC is also equal to 30 square units in its length. From one side, but from the other side, if we define the area of this green shape, that is the area that we are looking for in this question, as x, the area of this green shape is equal to x square units according to our definition. So in total, the area of the right triangle ABC will be equal to x plus 5. So from one side, the area of triangle ABC equals to x plus 5, from the other side it is equal to 30. From this equation, we derive that x plus 5 equals to 30. Here we subtract 5 from this equation, and we get that the area that we are looking for in this question, that is the area of the green shape, that is x, is equal to 30 minus 5 is 25 square units. And that is the answer to the question. Okay, again, I should find out that the area of this green shape that is equal to x is equal to 25 square units. So we finish with the second question. In the next step, on some of the lecture, we'll start with the first question, of course. Our mission in this first question is to find out the area of this rectangle ABCD. So in the drawing, we have the big rectangle ABCD. Inside the big rectangle ABCD, we have this semicircle. And in addition, we know that this is the big semicircle that we have inside rectangle ABCD. In addition, we know that this is line segment AP that is equal to 6 units in its length. This is line segment CP that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, because of the fact that ABCD is a rectangle, all those 4 angles inside rectangle ABCD are right angles. In the next step, we define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. We define the point of tendency of tangent DC with this semicircle. This point is point M. And finally, we defined the touching point of this semicircle with side AB of rectangle ABCD. This point is point E. In the next step, we join points O and M together by straight line. Point O is the center of this semicircle. Point M is the point of the semicircle itself. Therefore, OM is the radius of this semicircle that is equal to x units in its length according to our definition. And because of the fact that the radius OM that is equal to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle, and whenever your radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. By doing this construction, we can do the quadrilateral OMCB. Inside this quadrilateral OMCB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this surface again, in total it must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this surface again must be equal to 90 degrees in its side. So inside quadrilateral AMCBO, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So relate to this quadrilateral MCBO, it's a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle MCBO, side MO must be equal to the opposite side CB. But MO is X, therefore the opposite side CB must be also equal to X units in its length. In the next step, we join points P and E together by straight line. By joining points P and E, we can do peripheral angle APE. This is peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and we know that according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Therefore, this peripheral angle must be equal to 90 degrees according to rule 7. Here, AO equals to OE. They're both the radii of the circle, that equals to X. In the next step, by doing this construction, we're going to do the right angle triangle EPA. We define this angle as alpha. So in the right angle APA, this angle equals to alpha. This angle equals to 90 degrees. Therefore, this third angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third angle must be equal to 90 degrees minus alpha according to the third rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the big right triangle ABC, and angle A also belongs to the small right triangle APE. Therefore, angle A is a common angle that belongs to both triangles. In the next step, we proved that the big right triangle ABC is similar to the small right triangle APE. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, both those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, this is angle A, that is a common angle that belongs to both triangles. So we can write down that angle A equals to itself is a common angle that belongs to both triangles. So we should prove that all the angles of the big right triangle ABC are correspondingly equal to all the angles of the small right triangle AP. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the right triangle APE or side AB of the big right triangle ABC is equal to side AE of the small right triangle APE or side AC of the big right triangle ABC. So I'll repeat again. We will derive that side AP of the big right triangle APE or side AB of the side AP of the small right triangle APE or side AB of the big right triangle ABC equals to side AE of the small right triangle APE or side CA of the big right triangle ABC. AP is 6 according to what is given as the question. AB is the missing side, so many letters it is. AE is 2x, it is the diameter of the semicircle. AE is 2x, and CA in total equals to 5 plus 6, that is 11. So CA equals to 11. So in total, we found out that 6 over AB equals to 2x over 11. Here we cross multiply this equation and finally found out that 6 times 11 equals to 2x times AB. 11 times 6 is 66, and it is equal to 2x times AB. Here we divided this equation by 2. We actually found out that 66 over 2 is 33. That is equals to 2x over 2 is x. So in total this expression equals to x times AB. So we actually found out that 33 equals to x times AB. Here we divided this equation by x. So as I mentioned before, we can divide this equation by x because x is the diameter of this semicircle. It can never be equal to 0. So we divided this equation by x and finally found out that AB equals to 33 over x units in its length. That is to say, the length of the side AB is 33 over x. The width is BC, that is X. The width of rectangle ABCD, of course. Again, our mission is to find out the area of this rectangle ABCD. Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. Therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length is AB, the width is BC. Repeat again. The length is AB, the width is CB. AB is 33 over X, BC is X. So in total, the area of rectangle ABCD equals to 33 over X times X. We have X in the numerator and X in the denominator. So X will get cancelled and we left only with 33. So in conclusion, we found out that the area of this rectangle ABCD is equal to 33 square units. We finished with the first question. In the next step, I present to you the second question. We will solve the second question of this lecture. Our mission in this second question is to find out the area of this green shape. So in the drawing, we have this is square ABCD, and we also know that this is a triangle OPC. The area of this triangle OPC is 5. And again, our mission, and we also know that BP equals to PC. So again, our mission is to find out the area of this green shape. Because of the fact that ABCD is a square, and we define the length of BP as A and the length of PC as A. So BC is 2A. Therefore, we know that all the sides of a square are equal to each other. Therefore, AD must be also equal to 2A. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if this angle is theta, then this angle must be also equal to theta because they are equal to each other. We know that the opposite sides of a square are parallel to each other. That is to say, AD parallel to BC and AB is parallel to DC. Those two angles are defined as alternating angles and they are located between the parallels AD and BC, and therefore according to rule 15 they are equal to each other. So if this angle is alpha, then this angle must be also equal to alpha because they are equal to each other according to rule 15. Likewise, those two angles are also defined as alternating angles and they are located between the same parallel lines AD and BC, therefore they must be equal to each other according to rule 15. So if this angle is beta, then this angle must be also equal to beta because they are equal to each other according to rule 15. So it is very easy to see that we actually prove that the big triangle ADO is similar to the small triangle POC according to angle similarity rule. In both triangles we have angle alpha, in both triangles we have angle theta, and in both triangles we have angle beta. So those two triangles are similar to each other according to angle similarity rule. And from the fact that they are similar to each other, we can implement here rule 22. Okay. So what is rule 22? According to rule 22, if we have those two similar triangles, then the ratio between the areas of those two similar triangles, that is to say the area of triangle ABC of the, over the area of triangle EDF, is equal to the square of the ratio between their corresponding sides. The first pair of corresponding sides is AC over DA squared. Likewise, we have the other corresponding sides is AB over DE squared over EF. DAB over DF squared, and the third corresponding sides are CB over EF squared. So in total, according to rule 22, the ratio between the areas of two similar triangles is equal to the square of the ratio between their corresponding sides. So can actually implement rule 22 in our drawing. Why? Because of the fact that we found out that those two triangles are similar to each other according to angle similarity rule. And therefore, according to rule 22, the ratio between their areas must be equal to the square of the ratio between their corresponding sides. And again, according to rule 22, the ratio between the areas of the two similar triangles, that is to say, the ratio between the area of triangle DOA or the ratio of the triangle POC is equal to the square of the ratio between their corresponding sides. Side AD is the corresponding side of side PC. So AD over PC squared, AD over PC squared is equal to the ratio between the areas of the two similar triangles according to rule 22. Again, this equation is the implementation of rule 22 in our drawing. So the area of triangle AOD over the area of triangle POC. The area of triangle POC is 5 according to what is given as the question. And it is equal to AD. AD is 2A. AD is 2A over PC. PC is A. So it is 2A over A squared. We have A in the numerator and A in the denominator, so A will get cancelled, and we left only with 2 squared, that is 4 of course. In total, we actually found out that the area of triangle DOA over 5 equals to 4. If we multiply this equation by 5, and finally found out that the area of the big triangle DOA equals to 5 times 4, that is 20 square units. So this is the area of the big triangle. The area of the big triangle DOA, this triangle DOA is equal to 20 square units. Okay? Because of the fact that the big triangle DOA is similar to the small triangle POC, the following relationship exists between their sides. This is to say, side AD in triangle ADO over side PC in triangle OPC is equal to side AO of triangle DOA over side OC of triangle OPC. But again, because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of the big right triangle AOD over side PC of the small right triangle POC equals to side AO of the big right triangle AOD over side OC of the small right triangle OCP. AD is 2A over PC. PC is A, and it is equal to AO over OC. We have A in the numerator and A in the denominator, so A will get cancelled, and we left only with 2 in this side of the equation. So in total, we found out that 2 equals to AO times OC. Here we multiply this equation by OC, and finally found out that 2 times OC equals to AO. So if we define OC as B, and we substitute OC by B, we get that OA is 2B. So if OC is B, then OA is 2B. That is to say, OA is twice as long as OC. So if OC is B, then OA is 2B. Okay? Now, I actually presented to you a new rule and implemented the new rule in our drawing. The new rule is as follows. This is triangle ABC that could be any triangle. If we draw the red line segment AP, it will divide the triangle ABC into two smaller triangles, triangle ABP and triangle ACP. The area of this triangle ABC is equal to the base of the triangle that is BP times the height that is edge over 2. Repeat again, the area of triangle ABP is the base BP times the height edge over 2. The area of this triangle APC is equal to the base PC times the height that is edge. Both triangles have the same height that is edge over 2. So the area of triangle ACP equals to the base PC times the height edge over 2. So if we divide the areas of those two triangles with each other, the ratio between the areas is actually BP times edge over 2 over the area of triangle APC, that is CP times edge over 2. We have 1/2 on both sides, on the numerator and the denominator, so 1/2 will get cancelled. We have edge of both the numerator and the denominator of this expression, so edge will get cancelled, and we left only VP over CP. That is to say, we found out that the ratio between the areas of those two smaller triangles is equal to the ratio between their bases. Why? Because it is BP that is the base of triangle ABP over PC that is the base of triangle APC. So the ratio between the areas of the small triangles is equal to the ratio between their bases. So we can implement the new rule in our drawing. One put in our drawing, we have this is triangle ADC, this is the right triangle ADC, and 9/7 OD divides the right triangle ADC into two smaller triangles. The first small triangle is ADO and the second smaller triangle is DOC. So we can implement the new rule in our drawing. We get that the ratio between the area of this small triangle AOD over the ratio between the area of this small triangle ODC will be equal to the ratio between their bases. We choose the base of triangle AOD is AO, and we choose the base of triangle OCD is OC. So in total, we can find out that the ratio between the area of the small triangle that is ADO over the area of the other small triangle that is OCD, it is equal to the ratio between their bases. We choose the base of this triangle ADO as AO, and we choose the base of this triangle DOC is OC. So it is AO over OC. Again, the ratio between the areas of the smaller triangles, it is equal to the ratio between their bases. Okay, but we have already found out that the area of triangle ADO is 20, and the area of triangle OCD is the missing area, so we leave it as it is, and it is equal to AO. AO is 2B. AO is 2B over OC. OC is B. OC is B. So in total, we should find out that 20 over the area of triangle OCD equals to 2B over B. We have B in the denominator and B in the denominator, so B will get cancelled, and we left only with 2. So in total, we should find out that 20 over the area of triangle OCD equals to 2. So here we divided this equation by 2, and we multiplied by the area of triangle OCD simultaneously. And we found out that we multiplied this equation by the area of triangle OCD, so we have the area of triangle OCD here, and we divided by 2. So here we have 20 over 2, that equals to the area of triangle OCD. 20 over 2 is 10. So in total, we found out that the area of this small triangle DOC is 10 square units. Okay. This triangle ADC, the right triangle ADC, can go to this triangle, the right triangle ABC, according to side rule. So why those two right triangles can go into each other? First of all, side DC or triangle ADC equals to side AB or triangle ABC, because it is a square. In addition, side AD or triangle ADC equals to side BC of triangle ABC for the same reason. And AC is the common side that belongs to both triangles. So AC equals to itself. So if we found out that triangle ADC can go into triangle ABC according to side rule. Okay, repeat again. We actually found out that triangle ADC can go in, this is the sign of congruent, to triangle ABC according to side rule. And because of the fact that triangle ADC can go into triangle ABC, we can derive from it that they have also the same areas. So the area of triangle ADC is equal to the area of triangle ABC. But we have already found out that the area of triangle ABC and the area of triangle ADC is 20 plus 10, that is 30 square units. So we can write here that the area of triangle ADC is equal to 30 square units. From one side, the area of triangle ADC equals to 30 square units. And from this equation, 30 equals to the area of triangle ADC equals to the area of triangle ABC, we derive that the area of triangle ABC is 30 from one side, but from the other side, the area of this triangle ABC, if we define the area of this green shape as x, so in total the area of triangle ABC must be equal to x plus 5, because the area of this triangle is 5 square units. So from the other side, the area of triangle ABC equals to x plus 5. Again, from one side the area of triangle ABC is 30, from the other side is x plus 5. And from this equation, we derive that x plus 5 equals to 30. Here we subtract 5 from this equation, and we found out that x equals to 30 minus 5, that is 25. So in total, we found out that the area of this green shape, that is x, is equal to 25 square units. Okay, thank you very much.